I want to speculate a little bit about what the graph might have looked like. This video ties in with the opening door video, all right? So a couple of things here. On the y-axis, we have degrees, okay? How many degrees the door is open, okay? And if you watched carefully, the door opened a little bit more than a 90-degree angle. It actually opens about that wide. So it'll maybe go up to like, 110 or something like that degrees. The door was closed at 0 seconds, okay? I think the whole thing took maybe 3 or 4 seconds. So this starts out at the point 0, 0, okay? And I ask you to kind of envision what you think this might have looked like, and your graph might look a little bit different than mine. What I was trying to do was open the door at a pretty constant pace, okay? So we got this, kind of pace that was going like this. Maybe the door went like this, and then it immediately hit the wall. And the angle started to decrease because it bounced back and it went the other way. But if you noticed, once it hit the wall, it got slower and slower and slower as it closed. So it didn't just open, hit 110 degrees and then close. It kind of did this sort of thing, and it just kind of tailed off. And in fact, one of the times the door actually never closed. It just kind of kept extending out. We could almost say it was approaching an asymptote as opposed to actually closing. Okay, and in one case it did actually close. In that case, it would actually hit the axis there. But this is the kind of thing that happened. Okay. What Forrester is going to be doing is he's going to be giving you a scenario that's a little bit similar to this, okay? I don't think the graph looks exactly like this. He's going to have you graph it, though. I think his graph is going to go more like this. I think it's going to be, it's an automatic door opener, and it's one where the door kind of pops open slowly and then kind of eases shut. So I think it's going to be more like this sort of thing, where you don't really have any straight lines or any constant rates. Anyway, what Forrester's going to be asking you to do is to estimate the rate of change in degrees per second of the door as it opens, at some point where it opens. And what Forrester's going to have you do here is he's going to have you use the average rate of change. Remember, the average rate of change is the rate of change over the entire time interval. Okay, technically the average rate of change is f of b minus f of a all over b minus a. But he's going to be having you use the average rate of change to estimate the rate of change at an instant. Okay, if you remember, the instantaneous rate of change is how fast something is moving at a split second in time. How many degrees per second was the door opening maybe when we were 2 seconds into the door opening, something like that. Okay, physically on a graph, that instantaneous rate of change, for example, if I was talking about the rate of change at 2 seconds, that would be the slope of that line on the curve right there. Okay, but because it's a curve, it's not a straight line, we don't know how to find the slope at a point on a curve. Okay, the concept here that we're going to use is to try to pick values that are very, very close together. For example, if I start out at a point here at 2, so maybe I have the point 2, f of 2, okay? And if I go real close to that point right there, maybe at the point 2.1, comma, f of 2.1, the slope that would go through those 2 points is very close to the slope of the overall line at that point. It's not perfect, but it's pretty decent, okay? Or maybe I could pick a point behind the point 2f of 2. Maybe I could come back here at this point back here, 1.9, f of 1.9. And I can find the slope between those 2 points. Or maybe I could pick points that are even closer. Maybe I could pick a point at t equals 2 and t equals 2.01 or 2.001. And I could try to calculate the slope. And the idea here is as we pick points that are closer and closer and closer together, we're going to get a more accurate idea of what the actual slope is. All right, so Forrester's going to have you kind of investigate that. I think he's going to have you use a function that he gives you. He's going to ask you to use the table on your graphing calculator to generate these different values very quickly. So hopefully you know how to put a function in, you know how to find that. If you're doing anything with trig values, make sure your calculator is set in radians. We will be using radians mostly this year in calculus if that comes into play. Also, if you're making a graph, pay attention to what kind of information's on the x-axis, what kind of information's on the y-axis. You may need to adjust your window a little bit to get everything in your graph to fit correctly. So for example, in my door opening one, if I had the equation, which I don't, I probably would have had the y-axis go to maybe like 120, something like that. The x-axis, probably at least 3, but maybe going out to like 5, 6, 7, however long you think that it took for the door to shut. Okay, and there's a little guess and check sometimes when you try to do that. So that's a little bit of an overview of where we're headed. And of course, I'll have other videos talking about other topics. Section 1.2 and 1.1 are really going to go pretty closely together. 1.1 is kind of an investigation that leads into the discussion of average rate of change versus instantaneous rate of change in section 1.2. So I hope that kind of helps get things started.